History is often written by the victors, but the most profound and devastating chapters are sometimes dictated by the unintentional villains of progress. Imagine a single human being, a man of exceptional brilliance and industrial ambition, whose signature is etched into the very atmosphere of our planet and the bloodstreams of every living creature. This individual was not a conqueror or a tyrant in the traditional sense, yet his inventions would go on to claim millions of lives, degrade the collective intelligence of the human race for generations, and trigger a global environmental catastrophe that we are still desperately fighting today. It is a haunting paradox of modern science that the pursuit of efficiency and comfort can lead to a silent, invisible decay. We often speak of the atomic bomb as humanity's most dangerous creation, but the inventions of Thomas Midgley Jr. were far more insidious because they were marketed as essential advancements. They were sold in every corner store and pumped into every car, slowly eroding the cognitive potential of children and fueling a decades-long wave of violent crime across the globe that baffled sociologists for years. To understand how we arrived at this precipice of self-destruction, we must first look at the shadow cast by Claire Patterson, a geochemist whose work would eventually unmask the horror of the 20th century. Before his discovery, the world was blissfully unaware of the poison in its veins. The context begins in the high-stakes world of post-war science, where technology forged in the fires of conflict was being turned toward the mysteries of the universe. During the 1940s, the Manhattan Project had pushed the boundaries of physics, using massive mass spectrometers to separate isotopes of uranium-235 for the world's first nuclear weapons. When the war finally ended, these powerful tools were repurposed for civilian research. Patterson, a meticulous and driven young scientist, embarked on a quest that seemed purely academic at the time. He wanted to determine the exact age of the Earth. To do this, he relied on the steady, ticking clock of radioactive decay. Uranium atoms, over billions of years, predictably transform into lead. By measuring the ratio of uranium to lead within ancient crystals, a scientist could theoretically calculate the precise moment our planet was born. Patterson began his research at the University of Chicago, working alongside his partner, George Tilton. Their focus was on durable minerals called zircon crystals, extracted from billion-year-old granite. These crystals were the perfect time capsules because, during their molten formation, they accepted uranium into their lattice, but naturally rejected lead. This meant that any lead found inside a zircon crystal today had to be the result of uranium decaying over eons. There should have been no initial lead present at the start of the clock. George Tilton handled the uranium measurements with ease, producing perfect, consistent data every time. However, when it was Patterson's turn to measure the lead, the results were a chaotic and frustrating nightmare. Every sample he tested came back with lead levels that were impossibly high and wildly inconsistent. It was as if the very air he breathed was saturated with the heavy metal. No matter how many times he scrubbed his equipment or distilled his acids, the extra lead remained, haunting his data like a ghost in the machine. Before we continue the story of how this laboratory anomaly revealed a global conspiracy, subscribe to the channel and tell us in the comments where you are watching from. This mystery of the vanishing accuracy was not just a technical glitch. It was the first crack in a wall of corporate secrets that had been built over decades. Patterson became obsessed with finding the source of the contamination. He built what would become the world's first ultra-clean lab, sealing the doors, filtering the air, and even acid washing his own clothes to ensure that not a single speck of dust could contaminate his samples. It took years of isolation and obsessive cleaning, but eventually, he achieved the impossible. He successfully measured the age of the Earth at 4.55 billion years, a figure that stands to this day. But in doing so, he stumbled upon a much more terrifying reality. The reason his previous experiments had failed wasn't due to his lack of skill. It was because the entire world had been doused in lead. The levels he was finding in the environment were thousands of times higher than they should have been naturally. The mystery of where all this extra lead was coming from would lead him back to the early days of the automotive industry, and a man whose solution to a common mechanical problem would become a death sentence for the planet. While Claire Patterson was uncovering the invisible shroud of lead decades later, the origin of this global contamination traces back to a tragedy on a cold winter day in 1908. On the Belle Isle Bridge in Detroit, a car stalled, leaving the driver stranded in the freezing air. A man named Byron Carter, a close friend of Cadillac's founder, Henry Leland, happened to be passing by and stopped to help. In those days, starting a car was a grueling physical feat. It required a manual hand crank at the front of the engine, which had to be turned with significant force to ignite the combustion cycle. As Carter leaned in to crank the handle, the engine backfired. The heavy iron crank kicked back with terrifying speed, striking Carter directly in the jaw. The impact was devastating, shattering bone and leaving him in agony. Despite the best medical care of the era, gangrene and pneumonia followed the trauma. Byron Carter, a man simply trying to perform an act of kindness, died as a result of the very machine he had helped pioneer. The loss of his friend left Henry Leland consumed by grief and a burning sense of responsibility. He stood over Carter's grave and made a solemn vow. The Cadillac would no longer kill the people who drove it. He was determined to eliminate the manual crank forever, seeing it as a deadly relic of a bygone age. To achieve this, Leland turned to a brilliant electrical engineer named Charles Kettering, the head of research at General Motors. Kettering was a visionary who lived to solve the impossible. By 1911, he had developed a prototype for the electric self-starter, a revolutionary device that allowed drivers to start their engines from the safety of the cabin with a button. It was a monumental success. When first appearing in the Cadillac Model 30, it didn't just save lives, it opened the world of driving to everyone. However, this triumph inadvertently birthed a new, invisible, mechanical monster that would haunt the engineering world for years. This invention was heralded as a miracle, but it masked a deeper vulnerability. As car engines became more powerful, engineers began to increase compression ratios to squeeze more performance out of every drop of fuel. But this progress hit a noisy wall known as engine knock. When the piston compressed the air-fuel mixture, the heat and pressure sometimes caused the gasoline to ignite prematurely before the spark plug could fire. This resulted in a sharp metallic pinging sound that resonated through the engine block. It wasn't just an annoying noise. It was the sound of an engine destroying itself. This spontaneous combustion created violent shock waves that hammered against the pistons, leading to reduced power, terrible fuel efficiency, and eventually catastrophic physical damage. In the early 20th century, high-performance luxury cars were particularly susceptible to this, and the industry was desperate for a solution that didn't involve expensive redesigns of the entire engine architecture. The sound of knocking was more than a nuisance. It was a symptom of an underlying chemical instability. The problem lay deep within the chemistry of the fuel. Gasoline is a mixture of hydrocarbons, and not all molecules are created equal when resisting intense heat and pressure. Scientists categorize fuel based on octane ratings, a scale of stability under stress. On one end was N-heptane, a fuel that knocked easily, assigned a value of 0. On the other end was isooctane, highly resistant to detonation, assigned a value of 100. Gasoline engines required precision and stability to function smoothly. The refining processes of the time were primitive, producing low-octane fuel that struggled to keep up with modern high-compression engines. Oil companies and manufacturers like General Motors faced a crossroads. They could invest in advanced refining to naturally increase octane, or find a cheap secret additive to tame the gasoline. This search for a shortcut would lead them to a young engineer named Thomas Midgley Jr., setting the stage for a discovery that would solve the knocking problem while poisoning the very air humanity breathes. Thomas Midgley Jr. He was a 27-year-old mechanical engineer with a restless mind. When Charles Kettering tasked him with finding a solution to the persistent engine knock, Midgley dove into the project with a fervor that bordered on obsession. Working out of a laboratory in Dayton, Ohio, he transformed himself from a traditional engineer into a self-taught chemist, surrounding himself with beakers, test tubes, and a chaotic array of chemical compounds. His approach was largely if he didn't know the theory, he would simply test every substance he could find until something clicked. He was an outsider to chemistry, a fact that allowed him to ignore conventional warnings and experiment with hazardous materials that seasoned chemists might have avoided. The early days of his research were a parade of bizarre and failed experiments. Midgley and his small team tested thousands of different chemicals, hoping to find the magic ingredient that would stabilize the combustion process. They tried everything from iodine to melted butter, camphor, and even ethyl acetate. Some substances showed promise, while others were utterly useless, but nothing provided the consistent, cost-effective result that General Motors demanded. The laboratory became a graveyard of failed theories, littered with half-finished reports and chemical residues. He was driven by a belief that the answer lay hidden somewhere within the periodic table, waiting for a persistent enough mind to uncover it, regardless of how many failed attempts stood in the way. During this exhaustive search, Midgley discovered that ethanol was actually an excellent anti-knock agent. It was clean, renewable, and relatively easy to produce. If added to gasoline at a concentration of about 10%, it virtually eliminated the knocking sound and improved performance without damaging the engine. However, when Midgley presented these findings to his superiors, he was met with a cold, corporate wall. Ethanol was a well-known substance that had been around for centuries. It was impossible to patent. To the automotive giants, a solution anyone could manufacture was no solution at all. They didn't just want an engine that ran smoothly. They wanted a proprietary chemical they could control and sell for a massive profit. Undeterred by this rejection, Midgley pivoted back to more obscure chemical combinations. One of his more notorious experiments involved tellurium. While it was highly effective at suppressing engine knock, it came with a horrifying side effect. Tellurium possessed a potent, pervasive odor that was nearly impossible to remove. After working with it for only a few days, Midgley began to exude a sickening, garlic-like stench from his very pores. The smell was so overwhelming that it clung to his clothes, his hair, and even his breath. It became so unbearable that his own family forced him to sleep in a separate part of the house, and he found himself socially isolated, unable to enter a public theater without people recoiling from the smell. The breakthrough finally arrived in December 1921, a moment that would change the course of human history for the worse. Midgley turned his attention to a compound known as tetraethyl lead. It was a heavy, oily liquid that combined lead with organic molecules, allowing it to dissolve perfectly in gasoline. The results were nothing short of miraculous from a technical standpoint. Unlike ethanol, which required a significant volume to be effective, tetraethyl lead worked in incredibly small concentrations. Just 1 part per thousand was enough to transform low-grade gasoline into a high-performance fuel. It was odorless, cheap to produce, and most importantly for General Motors and its partners, it was entirely patentable. Midgley was ecstatic. He saw not just a solved engineering problem, but a golden ticket to wealth. He famously predicted that this single discovery would earn hundreds of millions for the companies involved. In his excitement, the young engineer chose to ignore the well-documented toxicity of lead, a substance known since Roman times to cause madness and death. To Midgley and the industrial titans, lead was simply a tool, a convenient chemical lever to move the world. They were blinded by the promise of progress and the allure of the bottom line, ignoring the fact that they were about to distribute a potent neurotoxin through the exhaust pipes of every car on the planet. The marketing machine behind tetraethyl lead was as brilliant as it was deceptive. Knowing full well that the word lead carried a millennium of stigma associated with Roman madness and the decay of the nervous system, Midgley and his corporate sponsors at General Motors made a calculated decision. They would never refer to the additive by its scientific name in public. Instead, they christened it ethyl. The name was soft and utterly misleading, evoking images of harmless grain alcohol or a friendly neighbor rather than a heavy metal poison. This linguistic sleight of hand allowed the company to bypass public anxiety and position their new product as a miracle of modern engineering, a clean addition to the future of transportation. To solidify their control over this lucrative market, General Motors joined forces with chemical giant DuPont and the oil behemoth Standard Oil of New Jersey to form the Ethyl Gasoline Corporation. This alliance of industry titans ensured that leaded gasoline would not just be an option, but an inevitability for every motorist on the road. The debut of ethyl was a masterclass in promotion. In May 1923, at the legendary Indianapolis 500, the roar of the engines told a story of industrial triumph. The cars that crossed the finish line in first, second, and third places were all fueled by Midgley's leaded additive. The message to the American public was clear. If you wanted power, speed, and the pinnacle of technology, you needed ethyl in your tank. The victory sparked a wildfire of demand. Gasoline stations across the country began installing special pumps for the premium fuel, and the public, mesmerized by the promise of smoother rides and more powerful acceleration, didn't think twice about the invisible exhaust trailing behind them. The invisible lead particles began to settle into the dust of the streets and the lungs of city dwellers. But the profits were so immense that any whisper of caution was drowned out by the sound of accelerating engines. However, the shiny veneer of progress soon cracked under the weight of human suffering. In 1924, at a manufacturing plant in Deepwater, New Jersey, the true nature of tetraethyl lead revealed itself in the most horrific fashion. The workers tasked with producing the concentrated additive started exhibiting bizarre behavior. Men who had been perfectly sane days earlier began swatting at the air, claiming they were being attacked by swarms of invisible insects. This prompted the chilling nickname for the facility, the House of Butterflies. The lead was attacking their central nervous systems, inducing a state of acute toxic psychosis. Within just 2 months of the plant's operation, 5 workers had died in fits of violent insanity, and dozens more were hospitalized, their bodies racked by tremors and their minds shattered. The media labeled the substance loony gas, and for a brief moment, it seemed the industry might be forced to halt its deadly experiment. Faced with a public relations catastrophe, Thomas Midgley Jr. stepped into the spotlight to perform a daring and dangerous piece of theater. In October 1924, he called a press conference to demonstrate the supposed safety of the chemical. Before a crowd of skeptical reporters, Midgley took a container of pure tetraethyl lead and washed his hands in the oily liquid. To further drive his point home, he held a bottle of the substance to his nose and inhaled the toxic vapors for 60 seconds, declaring that he could do this every day without succumbing to any ill effects. It was a performance of supreme confidence, designed to quell the rising tide of fear. Yet behind the scenes, the reality was starkly and terrifyingly different. Midgley was already secretly suffering from lead poisoning, his own body failing under the weight of the substance he championed. Shortly after his public demonstration, he was forced to flee to Florida for a long period of convalescence, desperately trying to purge the lead from his system in the fresh sea air, while the Ethyl Corporation continued to pump his poison into the global atmosphere. Despite the harrowing events at the New Jersey plant and his own brush with death, Thomas Midgley Jr. did not retreat from industrial chemistry. On the contrary, his reputation as the premier problem solver for the giants of American industry only grew. By the late 1920s, the automotive world was conquered, but a new, more intimate crisis was brewing within the average American home. The early era of mechanical refrigeration was a perilous time. While the ability to keep food cold was a miracle of modern life, the chemicals used to achieve this, ammonia, methyl chloride, and sulfur dioxide, were a toxic nightmare. These substances were not only corrosive but highly lethal, and in some cases, violently explosive. A simple leak in a kitchen refrigerator was a potential death sentence for a sleeping family. In one tragic incident in an Ohio hospital, a leak of refrigerant gas led to the deaths of over 100 people. The industry was at a standstill, and the Frigidaire division of General Motors was desperate for a breakthrough to save their investment. Once again, Charles Kettering turned to his most reliable engineer. He tasked Midgley with a clear directive: find a refrigerant that was non-toxic, non-flammable, and chemically stable. It was a tall order, one that many chemists thought would take years of experimentation. Yet, Midgley possessed a unique, almost instinctive grasp of the periodic table. He began by focusing on elements that were known to be stable and gaseous under pressure. With his team, he narrowed his search to the element fluorine. Historically, fluorine was considered dangerous and difficult to handle, but Midgley believed that when combined correctly with carbon and chlorine, it was the key. In an astonishing display of intuition and speed, Midgley and his colleagues synthesized dichlorodifluoromethane, later known as Freon, in just 3 days of work and high-stakes corporate research. It seemed that Midgley had achieved the impossible once again. He had created a substance that appeared to be the perfect chemical. It was odorless, it would not burn, and it would not poison anyone who breathed it in. To prove its safety to a world still wary after the loony gas scandals, Midgley returned to the public stage. At a meeting of the American Chemical Society in 1930, he performed a feat of showmanship that would become legendary. Before a packed audience of chemists and journalists, Midgley took a deep, theatrical breath of Freon vapor, filling his lungs with the clear gas. He then leaned over a lit candle and slowly exhaled. The flame was instantly extinguished by the inert properties of the gas itself. He stood there, smiling and unharmed, a living testament to the safety of his newly developed chemical creation. Freon, the first of many chlorofluorocarbons, or CFCs, became an overnight sensation. Within a few short years, it was everywhere. It wasn't just in refrigerators. It was in air conditioning units in cars, skyscrapers, and homes across the globe. It found its way into aerosol cans, powering everything from hairspray to bug repellent. Migley was hailed as a hero of the modern age, a man who had made the world more comfortable and safer for everyone. But hidden within the stability that made Freon so safe was an invisible, delayed action fuse that would eventually threaten the entire planet of the Earth. Because CFCs were so chemically inert, they did not break down in the lower atmosphere. Instead, they drifted slowly upward, migrating into the stratosphere over several decades. It would take decades for scientists to realize that once these molecules reached the upper atmosphere, they were broken apart by ultraviolet radiation. This released chlorine atoms that acted as a chemical scythe, all reaping the Earth's protective ozone layer. Migley had unknowingly launched a global assault on the shield that protects life. While leaded gasoline was poisoning the ground and blood of children, his CFCs were tearing a hole in the sky. Migley stood at his peak, unaware his triumphs would be remembered as destructive inventions. As the decades rolled on, the true cost of Thomas Migley's ingenuity began to manifest in ways far more insidious than a single explosion or a poisoned factory worker. The leaded gasoline that powered the American dream was quietly, relentlessly leaching into the blood of every child born into the modern world. This was the birth of what experts call the lead crime hypothesis, a chilling correlation discovered by researchers decades after Migley's death. They found that as lead levels in the atmosphere rose during the mid-20th century, so too did rates of violent crime, reaching a fever pitch in the 1970s and 1980s. Lead is a potent neurotoxin that specifically targets the prefrontal cortex, the part of the brain responsible for impulse control, focus, and emotional regulation. By flooding the air with lead, Migley had effectively lowered the collective IQ of the human race by several points and primed an entire generation for aggression. It was a silent global lobotomy performed 1 gallon of gasoline at a time, creating a legacy of cognitive impairment that would haunt the world for a long century. Enter Claire Patterson, the geochemist whose quest to date the Earth had accidentally uncovered the staggering scale of this disaster. Patterson realized that the extra lead he had found in his laboratory wasn't just a localized nuisance. It was a symptom of a total planetary poisoning. He found that modern humans had lead levels in their bodies hundreds of times higher than their ancient ancestors. When he attempted to publish these findings, the industry that Migley helped build did not go quietly. The Ethel Corporation, backed by the immense wealth of General Motors and DuPont, launched a ruthless smear campaign against Patterson. They tried to dry up his research funding, excluded him from government panels, and even pressured his university to fire him. For decades, Patterson was a lone voice screaming into a hurricane of corporate denial and orchestrated lobbying. He spent the better part of his life testifying before Congress and battling the same industrial giants that Migley had served so faithfully. Patterson's crusade finally bore fruit in the 1970s when leaded gasoline began to be phased out, leading to a dramatic and near instantaneous drop in blood lead levels worldwide. While Patterson fought to save the world from Migley's past, the inventor himself was facing a personal reckoning that no amount of chemical brilliance could solve. In 1940, at the age of 51, Thomas Migley Jr. contracted poliomyelitis. The disease was merciless, leaving him paralyzed from the waist down and confined to a bed, stripped of the mobility and vitality he once enjoyed. But the mind that had re-engineered the chemistry of the world could not stay idle. Even in his crippled state, Migley sought a technical solution to his physical limitations. He designed an elaborate system of ropes, pulleys, and heavy harnesses suspended from the ceiling above his bed. This intricate web of machinery allowed him to lift and reposition himself without the aid of nurses or family members. It was a mechanical marvel of his own creation, yet another invention intended to improve the human condition through engineering and ingenuity. On the morning of November 2nd, 1944, the tragedy of Thomas Migley Jr. reached its final, macabre conclusion. While attempting to use his complex pulley system, Migley became hopelessly entangled in the very ropes he had designed to set him free. In a cruel and sudden twist of fate, the harness tightened around his neck as he struggled. Unable to break free or call for help, the man who had inadvertently poisoned the atmosphere and scarred the Earth's ozone layer was strangled to death by his own invention. It was an end so heavy with irony that it seemed scripted by a vengeful deity. Migley died at 55, leaving behind a world that was technologically advanced yet fundamentally broken by his most dangerous corporate and chemical solutions. The legacy of Migley remains a final, haunting warning.